So I'm going to talk about work that I did with Uriel, Sergey, who's here, and Takeshi, who unfortunately did not make it for this conference. So this work has been going on for quite some time, and it has been recently published in Physical Review E. I should add that PRE did not like the word tiger in the title of the paper, but I retain it for this talk. Since, okay. So this is a quick outline of my talk. I will start with the issue of statistical mechanics and turbulence, which Uriel dealt with ad nauseum, so I think I might skip that. Then I'll look at Galerkin truncation. Then I would look at the tiger phenomena purely from the point of view of what you see if you perform certain experiments on truncated systems. I will concentrate on the 1D Berger's equation. Then at some length, I will deal with how such structures are formed, and I'm being vague here because I haven't defined what these structures are as yet. And then I will make some concluding remarks. In the paper and in the work itself, we dealt not only with the 1D Berger's equation, but also with the two-dimensional Euler equation. Takeshi was supposed to speak on that, but he's not here. I will explain in a few words, if we have time, what happens in the 2D Euler case. So it's a slide very similar to what Uriel had, so I guess I would skip that, except as Uriel stressed, there has been a long connection between equilibrium statistical mechanics and turbulence, which on the face of it, it doesn't, they shouldn't be having any connection.
Will you join with on the left?
Ah, okay, that question I can answer. So this is Hoff. That's DTD, and okay, so, but what I would like to point out is the following result. So that's what got me at least interested in this problem.
There's a rumor that Brachet is still alive, but he's complètement chocolat, as we say.
I'll skip that remark. So in 2005, there was this paper by Brachet, Marc Etienne, and his collaborators, and they looked at the truncated 3D Euler equation. What they found was something very interesting, and I have a picture from their paper. They found, so if we look at this plot, so the different lines correspond to different times in the simulation when they recorded the energy spectrum. Mark, you will correct me the minute I go wrong. And you found that as time, so this is the energy spectrum for the 3D truncated Euler equation. So at the lowest time, you found that there is this k-squared thermalized spectrum in the large K modes, and you have a Kolmogorov-like k41 spectrum preceding this. As time evolves, the k-squared spectrum becomes more and more developed, and the transition wave number from where k-squared start going left. And so at very large times, you will eventually end up with a k-squared spectrum. So this was work in 2005 in a PRL by Brachet. What's interesting is that in 1989, Kreikman actually had a remark, which I quote here in italics, on the truncated Euler system, and he suggested that something similar to what Mark and his collaborators observed would actually happen. Okay, so while it wakes up.
You have to set your mark in non-sleep mode.
Non-sleep mode?
Yeah.
Yeah, it was awake actually. On the laptop it was awake.
Oh.
Yes. Okay, so let's move on. So now the question is, what happens? So let's take the simplest example to try and understand better how such long-lived transients or how such thermalized states evolve. And the simplest equation that one could think of is the Galerkin truncated 1D Berger's equation. So we had started playing with this, and again, when I come to the next slide and show how the 1D truncated Burger's equation actually looks like, it's something that again Mark had worked it out probably a year or so before we started investigating, but anyway. So just to get the notations right, so the untruncated inviscid zero viscosity Burger's equation looks like this. Now we define a wave number kg, where g stands for Galerkin, and a projector pkg whose action is to project the field from the infinite dimension to a finite dimensional Fourier space up to wave numbers kg. Anything beyond kg is killed. There's nothing there. So the associated Galerkin truncated inviscid Burger's equation, how you get from here to here, is you use the projector on the nonlinear term, and you also project your initial conditions on a finite dimension space. So let me first show something which is, which might be nice to look at. I'm sure a lot of you have looked at this. So suppose this is your nice Burger's initial condition, some arbitrary initial condition, combination of signs. What happens when you let this system evolve under truncated dynamics? Let's play the game. So you see that things, okay, ignore these things, these are because of projection. You see it follows the behavior of the untruncated system very well till the first singularity, till you get the shock. The minute you get a shock, which happened time steps before this, you see wild oscillations in certain regions where you would not expect anything much to happen. If you were not looking at the numerics, and if I said that I truncate my Burger's equation and I find something really horrible happening, wild oscillations, the obvious guess would be it must be somewhere close to the shock. To our surprise, that is not the case. Initially, we had looked at a pure sine x initial condition.
Mark Etienne's surprise.
To Mark Etienne's surprise. My apologies, Mark.
He has a good eye. It's basically an experiment.
To Mark Etienne's surprise, Uriel wasn't surprised. we saw these weird structures happening somewhere pretty far away from where all major events are happening in the Burger's dynamics. So if we let the system evolve, you see that these oscillations tend to grow bigger. It's periodic bunch conditions, so they appear, go out from here and come back here. And slowly, as you let this thing evolve further and further, you eventually see that the shocks sort of, this contamination, for want of a better word, cover the whole simulation domain, and eventually you end up in a thermalized state, white noise-ish, if you wait long enough, and it does. So while this movie is running, so these structures which we saw, the violent oscillations, is what we call tigers for reasons which you will explain. Okay. So let's look at these structures more carefully. I start with an initial condition which is single mode. That's the easiest to follow. So I have one shock. It's not sine x, it's phase shifted so that things don't appear at the edge of this box, just for visual clarity. At t equal to 1, which is t star for the Burger's equation, when the singularity hits the real domain, you find this two-shock structure develop. As you go a little further in time, you see this bulge in the solution, and there's something interesting in this bulge. What you see is that this bulge appears not here at the edge of the box for certain side effects, edge effects.
Wait, this periodic boundary condition, there is no...
Yeah, I mean, okay, I'm just trying to make it a bit dramatic.
You don't want neither the shock nor the tiger to coincide with the...
Yeah.
So
I'm talking about a graphical
interval, because otherwise it's not.
Yeah, I understand, but
by a quarter period.
Yeah, the Bishop's comment was something I said, not about the graphical thing, I guess. But the interesting thing is you don't see much activity here, none at all actually. And you see this bulge which develop somewhere far away from the shock. If you look hard enough at various results of various simulations, you find something more interesting as you play with more initial conditions. you see that for every initial condition that we've tried, this bulge actually appears not out of the blue, but it appears everywhere where the velocity coincides with the velocity of the shock. That is an important observation, as we will see in the next few minutes. With time, this bulge grows, and even visually you can see that the ramp, which appeared very thin here, starts becoming thicker. It's not a graphical artifact, but that is real. So let's try to understand how this bulge comes about, and this bulge is what we call tigers, and let's try to understand how these tigers form. Okay, there is another observation that we made, and this is before we had much theoretical understanding. Let's look at an initial condition which gives rise to more than one shock. Not only that, there is something nice about this initial condition. What you see is that, as I had said, that for velocities which are coincident with the shock velocity, we see bulges. However, this point here also has a velocity which is the same as that of the shock, and you see nothing there. So, second conclusion, tigers are born not only at points which are co-moving with the shock, but they also need positive strain. So let me quickly run through certain phenomenological explanations. Most of this I've talked about, and then I become a bit more systematic later. So a localized strong nonlinearity acts as a source of truncation waves. I'm putting the cart before the horse a little, but we'll get there. Away from the source, and here by source I mean the shock, away from the source, wherever the truncation wave encounters a region in the solution which has the same velocity as the shock, things resonate and things pile up. These resonant interactions are confined actually to a small interval of width. And for small times, close to the time of the first singularity hitting the real domain, we see that they are confined to regions of a small width which scales with the Galerkin truncation wave number. And this, I remarked a short while ago, that in regions of negative strain, you do not have tigers because in regions of negative strain, there's a compression, you have wave numbers higher than kg, and they are killed. Okay, wait. I'll come back to sort of justify some of the remarks that I made in the previous slide, but let's look at something else which is more connected with this first slide that I showed about Maxwell. From tigers to thermalization. I don't know how visible this is, but there are blue lines and red lines. The red lines is the solution of the Burger's equation untruncated, so there are no Galerkin effects there. The blue lines is the solution of the truncated Burger's dynamics. What you see is that these tigers form, and in the next slide you will see that at times close to when the tigers form, they are really localized both in physical space and in Fourier space. As time evolves, they stretch with vection, for example, and things become less monochromatic and more white noisage. They become delocalized in both spaces. As time evolves, the blue line contaminates the entire simulation domain, and at large time you have thermalized states, although the untruncated Burgers still retains its shock structure. The other point that I would like to draw your attention to is that the truncated Burger's equation follows the shock dynamics of the untruncated ones very closely till, for example, you come to times 1.3, where you can clearly see that the shock of the truncated Burgers is displayed from the untruncated one. Before that, shock dynamics, shock mergers are well preserved. So let's look at the object called tigers, now that we've zoomed in. So you see these are very nice monochromatic oscillations. At short time, they appear as a bulge. So this plot is the truncated Burger's equation when I subtract out the untruncated solution. With time, the bulge thins. It gets thin, then it starts becoming asymmetric, and eventually it sort of collapses. And you see seeds of thermalized behavior, for example, in this, when you come to such times. You can already start to see non-monochromatic behavior. This transition is something which we haven't been able to explain as yet. We have some ideas, but it's not very concrete. You also see some interesting features such as these beading, such as these beads which form away, but that's getting too far ahead in the story. Quantitatively, what do we know? If we look at that bulge, that tiger bulge which forms close to T star, one can make a measurement of the height of the bulge and the width of the bulge. From our numerics, we spanned from about Galerkin truncation wave numbers of the order of 100 to 20,000. Actually, we went up to 40,000. And we see a fantastic scaling of the width of the bulge at the birth of the tiger at T star, and it scales as kg minus 1/3, which is something I had mentioned in my slide before. And the amplitude of the bulge scales as minus 2/3. Do we understand these power laws? Can we derive these power laws? Is there a theoretical understanding? Well, the width of the bulge, so I will flash this quickly, but we can discuss this during the questions. So the scaling of the tiger width, very briefly, can be explained from a phase mixing argument. The scaling of the tiger amplitudes, on the other hand, has a very feeble footing, which we explain through energy conservation, which you have to have in the truncated equation. I would say, I mean, there is a slightly more stronger result than just those arguments. The other question that we looked at is, what about weak solutions? And this was the start of playing this game, is does the truncated Berger's equation converge weakly to the entropy or the or the untruncated solution in the absence of viscosity? The way we did that numerically, and I'll come to Tadmor and Bardos's conjecture later, the way we did that is, for a test function, we took a low-pass filter. So we took the solution of the truncated equation, pushed it through a low-pass filter. In red, you see the entropy solution, and tried to see whether they agree. For two different values of kg, we find they don't. They don't converge probably to anything. And there has been some recent work by Bardos and Tadmor, I think Uriel knows about it better than I do, where they have a similar conjecture that the truncated Berger's equation probably does not weakly converge to the entropy solution. Okay, so well, I'm running out of time, so I will just give a sketch of whether what we did. Did we do anything more than just play games on the computers? Well, we tried. We tried hard.
3 years.
3 years we tried. And that's why you will see that we have 3 approximations, 1 for each year in our theory. So as far as we got...
You also have 3 minutes, so 1 per minute.
1 per minute, okay, great.
Yeah, per minute.
Yeah. Okay, so the way we approached this problem was to understand just the birth of the tiger, not how the tiger collapses, not the onset of thermalization as we know. To do that, this is sort of a rough sketch of what we did. The paper actually is quite long with details in the appendices. We worked with the discrepancy, which is the usual thing to do between the truncated equation and the untruncated equation. Then we decomposed the various fields into high modes and low modes, and then we got out effective equations, which actually sort of look something like this, which is easy to deal with. And these are the 3 approximations we made. We neglected the term u prime squared, which is a small term. We set the perturbation initially to 0, because at small time we expect things to be the same. And we took the untruncated solution to be frozen at its value at T star. Numerically, we checked that all 3 approximations are not bad. So, okay, for now you have to take my word, but in the paper we provide evidence why they are not bad. And so you end up with a system of equations which are easy to handle, and you can do Ostomoffer's style of work when you look at this sort of linear equation and look at this operator. But I'm running out of time, so maybe, yeah, well, probably I should finish rather than. Okay, so I'll just skip the hard part, which is that of the algebra, how we come to obtain the scaling laws precisely, apart from arguments. So in conclusion and perspectives, I would say that tigers provide a clue to the onset of thermalization. We of course do not have a complete understanding of this phenomena. The interesting observation is this: tigers do not modify shock dynamics, but modify the flow elsewhere, because tigers induce Reynolds stresses at scales, at mesoscopic scales, as Sergei is kind of calling them. And there is no weak limit of the Galerkin truncated solution as Kg goes to infinity. This is the work that I completely avoided, where we also show that the key features of the Tiger phenomena is present in the 2D truncated Euler equation. And I believe Mark, Giorgio, you all have seen something similar in your work on MHD. And there are some new results which seem to indicate that in 3D we might have a similar phenomena. What's common is that complex space singularities approaching the real domain within one Galerkin wavelength, which is just 2 pi over kg, those trigger such phenomena both in 1D and in 2D. And the last point that we would like to make is, it has been a great hope that is there a way to purge tigers, which is to get rid of them, which would provide us numerically a very good subgrid scale model for studying such inviscid limits. Tamar?
Thank you very much. Go ahead.
Yeah, so I guess I have one comment and two questions. So in couple of papers, the title is on the resolution of Gibbs phenomena. So there are a couple of papers like that, and people there quote that if you put enough artificial viscosity in your spectral method, then the solution will converge correctly to the entropy solution. So are you aware of those
Yes.
papers?
Of course, if you put in a slight amount of viscosity, artificial or not, most of this phenomena would not exist, things would damp out. And I am aware of various ways of converging. For example, there is work by Howe. Uriel Howe or Howe?
Yes,
Howe.
Howe.
Okay, that's not correct. No, I wanted to check the pronunciation. Who have played with similar systems where they add a small epsilon damping term and then they look at convergence. Yes. But in this case, we are strictly in the zero viscosity.
Yeah, so that comes to my other questions.
Okay.
So what happens if now you solve compressible Euler equation? Do you think you still compressible Euler? So you have density, velocity, energy. Do you think you will see the tiger there?
My guess is yes.
Yes.
If things are all right for compressible Burgers and they're all right for incompressible Euler, I would put my bet that we would get similar.
Yeah. Okay. So now you go to my last point.
Okay.
So now if you think about those artificial viscosity as a damping in the spectral space, so now you recall your people put this trick that they have this damping boundary layer to avoid reflection from boundary.
Sure.
So can I interpret the tiger as reflection in the spectral space?
As
reflection. So you have wave going and you hit the boundary and come back.
Yes, I mean those are some of the things that I mentioned in my last remark about tiger purging. Those are some of the strategies that we are trying to implement, or maybe not so much trying to implement, but at least we have in mind about how to encounter these animals because of their strong monochromatic nature in both spaces, physical and Fourier, at times very close to T star, or for the 2D Euler, of course, you don't have the T star. I mean, you have it, it's
Let me just say one word about that. Already in the 70s, when I was working a lot with Steve Wossard, he had discovered that it's better to put sponges in Fourier space than things which would absorb things rather than reflect them back. Now what is happening is that tigers, you can look at them in Fourier space, they don't appear immediately. It takes a little while until they appear. And you have to wait until you have a boundary layer in Fourier space near the kg.
This is what Uriel is talking about, which I didn't have time
before you start purging them away. Yeah. Because if you just truncate things all the time, it's just the same thing as if you lower the truncation rate, remember, and then you don't get rid of any artifacts.
I have a question. Can you put the conclusion back again?
Yeah.
Okay. If I understand correctly, you are suggesting that this phenomena is somehow important to describe thermalization in the polarization.
I would say how you go to a thermalized state from very smooth solutions. Yes.
Now, a long time ago, almost 20 years ago, what we did was to use the lattice gas.
What is that?
I will explain you.
Something
the
like
lattice gas for a two-dimensional simulation, where we did observe the same thermalization that has been observed in the Navier-Stokes equation. And
sorry, by same you mean you observed long-lived transients which had a tail which
goes up. Okay, so when the system, if you wait enough, the minimum will move on the large scale, and then you have the repetition on the small scale. Now, my question is, now at that time, the simulation were done on resolution 8,000 square, which, considering now it's very low for the lattice gas. But my question is, do you think that something similar to a tiger should be observed also for this particular case? I mean, it's a rather general feature, or it depends on the way you are simulating the flow?
I think you can show your other picture.
No, but what we have done, and for which I can make a remark which is not answering your question at all, is that we have looked at the 2D Euler but via pseudospectral methods, and where we do see signatures of the onset of thermalization very similar to what you see in the 1D builders. However, you're talking about simulating the 2D Euler equation using a method different from pseudospectral. So I can't even make a very informed guess about how the projector and the projection will work in this system. Maybe Uriel or something can help me out on this.
Here. Lattice gases microscopically are like the real molecules in the world, a conservative system.
Yeah, so I don't think they provide always effective dissipation.
They do thermalize, there's no doubt. So does the motion in this room. If you wait long enough and close all the doors, it will thermalize. Okay. The truncated Euler equation is giving you some kind of fake microscopy. It is building its own, artificially its own world, which is in the
which is not there built into the thing.
And it's quite different from what you have in the lattice gas. But there are some anomalies.
Yes, but I really wouldn't. Okay.
Push them too far.
Okay. That's a photograph for Uriel. Uriel. This is one I took 3 years ago in a zoo.
Yeah.
About tigers fighting.
Uriel is on the left.
This must be Uriel. I can certainly say that this is Takeshi and me. So Uriel, Takeshi and me being
Look at the great wall.
Okay, thank you very much.
Thank you.